Lab 4 Oscillation. The purpose of this lab is to observe the motion of a spring mass system where the object swings in an arc while oscillating. In our example, our spring primarily oscillated left and right. In addition, we are examining the changes in energy of the spring mass system. To do this, we are using Newton's second law, which is F net equals mass times acceleration, which includes the force of gravity and the force of the spring, as well as the energy principle, which is E system equals work of the surroundings plus heat, where heat is negligible. The energy principle states that the total energy is equal to all the sums of the changes of energy. We are looking at the potential energy of the spring, gravity, and kinetic energies that add up to zero according to the energy principle. The experimental setup of this lab was to observe the motion of a swinging object that was released from rest, then would move in an arc and oscillate. I tracked the object's motion and collected data using Tracker, and I set the origin calibration stick from the fixed point given and measured down to the object, which was 0.700 meters. I started tracking at frame 6, which was the last frame the object was at rest before it started its arcing motion. I stopped when the video ended to collect a lot of data points. The initial velocity was 0 because it was at rest, and the initial position was negative 0.110 in the x direction, negative 0.623 in the negative y direction, and 0 in the z direction. For each frame, the object's motion was recorded by using the point mass tool. Next, I determined the spring constant and relaxed length L0 by using the period of oscillation, which is 2 times pi times the square root of the mass divided by the spring constant. However, first I determined T by taking 3 oscillations, then dividing it by 3 to give 1.524 seconds, as in the edX videos. Then I rearranged the equation to determine the spring constant, which is 6.83 newtons divided by meters. Secondly, to determine the relaxed length, I set the force of gravity equal to the force of the spring, then rearranged the equation to solve for L0, and using the spring constant and time previously determined to solve for the relaxed length, which is 0.123 meters. In Python, I used my data from Tracker to input the mass, initial velocity, and my first x and y positions into my initial conditions. And I updated the code so Python could make a graph with the force of gravity and spring and the energies for the energy principle. With the code updated, I was able to input the net force for the potential energies of the spring, kinetic energy, and gravitational energy, which is E equals K plus UG plus US. Then I was able to define my energies to find the total energy of the system, but first I found that the net force was F grav plus F spring, and I updated the position of velocity in Newton's second law. With the updated position, I was able to find the updated length and direction of the spring. Using the computational model, the program produced a graph with multiple lines indicating the different energies acting on the mass system. Specifically, blue is the kinetic energy, green is the change in potential spring energy, and red is the change in potential gravitational energy, and the orange is the change in total energy. The total energy remains around 0, which shows the energy principle at work. However, there is human error most likely when tracking the object in Tracker for the kinetic energy, because around 4 to 5 seconds the waves expand out compared to beginning and end of the data points. However, the potential gravitational energy and the spring energy look correct. As the spring energy increases, the gravitational energy decreases, and vice versa. Therefore, the model data is somewhat accurate to the computational model observed. Discussion questions. Number 1. Yes, the energy principle is satisfied by looking at the graph. The total energy remains around 0, which supports the energy principle's definition, where all energy should add up to 0 for delta E equals W surroundings. Discussion question 2. After determining the period of oscillation for the x and y components using the same method as earlier, the x position period of oscillation was 1.587 seconds, while the y position period of oscillation was 1.238 seconds. The times are similar and only off by 0.300ths of a second. The oscillation for the y is faster because we are primarily looking in the y direction, as well as the object moved left and right rather than up and down, so the period of oscillation was faster in the y direction.